As my colleague mentioned about the power-to-X is a crucial solution to replace fossil fuels because of the climate challenges. In power-to-X, renewable energy used for split the water in hydrogen and oxygen, that hydrogen can be used directly as a fuel or as a raw material in different industries, or can be participate in synthesis processes. Hydrogen from electrolyzers combined with nitrogen in synthesis process to produce ammonia. Ammonia can be used as a fuel or in fertilizer processes. Or hydrogen can be combined with CO2 captured from different industries in synthesis processes to produce carbon-based fuels. That methanol is one of the carbon-based fuels. In this project, our focus is hydrogen, ammonia, and methanol as a fuels. Each of these fuels has own challenges, practical challenges. For example, hydrogen has a very low minimum ignition energy. It's 100 times lower than propane. I put propane and gasoline here to make better sense of the fuels that our target. And also flammable limit for hydrogen is very wide, 4 to 75. Whereas for propane is very narrow, 2.2 to 9.9, 9.5. And it means with considering these two properties, it means hydrogen has very high explosion potential. And also with human sense, detection of hydrogen is impossible. It's colorless, odorless, tasteless, and even because of the density of hydrogen that is very low, we cannot add any additive, same as main captain that add to natural gas to make to detect with human sensitive. And also for hydrogen, it's invisible flame. It has an invisible flame. For ammonia, it has high ignition temperature. It means when we want to burn ammonia before combustion, hydrogen temperature must be go up. I mean, it needs preheating. And hydrogen is poison, and in some cases, led to NOx emission. Now a lot of researchers are working to optimize the ammonia combustion. And most challenges for methanol is invisible flame of burning the ammonia that my colleague Adina will talk more about the methanol. And this is why we want to do here, in order to address any safety for any potential accident related to these fuels that must be fully understood. So we want to do some experiment to show flame behavior, explosion behavior, what is the consequence of any accident. So for stepwise in the project, we divided in two subjects, burning and explosion, for different fuels. For example, for hydrogen, the first step is burning hydrogen in very small scale, in low pressure. That is, the main purpose of this step is learn to manipulate hydrogen. And then the step 2 is jet firing of hydrogen in different pressures, in different nozzle diameters. And in this step, we want to measure, for example, flame length, and we want to collect data for our future modeling simulations. And for ammonia, we want to burn in a small scale, pure ammonia. And as I mentioned, as one of the challenges for ammonia, that is have a high temperature, ignition temperature. Mostly now, ammonia mixed with other fuels, for example, hydrogen, propane, methane. That here we want to burn ammonia with other fuels to see the flame behavior or other things. Yeah. And for methanol, we have pull fire of methanol in different scales and with different concentration. In explosion experience, the first step is micro explosion of mixing hydrogen and air. And the next step, it's larger scale. Again, in the second step, we want to collect some data, and we want to measure pressure, and we want to use high-speed camera. For ammonia, we don't have any plan for explosion, and for methanol, micro vapor cloud explosion and vapor cloud explosion in larger scale. Today, I want to show some results for a small burner for hydrogen and micro explosion, and my colleague will be present pool fire of methanol. Adina, yeah. Yeah, for demonstration of hydrogen burner, we build a setup, and also we use propane as a reference to compare the flammability of flame behavior of hydrogen and propane. The setup part is gas cylinder, hydrogen and propane, regulator, burner, small burner, igniter, portable gas detector for safety, and thermocouples. And for monitoring, we use regular camera and thermal camera. And also, we measure the temperature in different positions of the flame. Here, we burn hydrogen in 3 different conditions: indoor, daylight, outdoor, daylight, and dark room. This is the flame of hydrogen in indoor. It's a little visible, and we try to keep condition for propane and hydrogen approximately the same. But you can see visibility of propane is much, much more than hydrogen. And interesting thing is when we burn hydrogen outside, it's very difficult to detect. It's completely invisible. And this is the results in dark room. Yeah, as I mentioned, one of the purpose to see invisibility and other properties of the flame. And also here, you can see it's orange color, but when we go to the reference literature, we can see that they wrote that it's a pale blue. But I think this color comes from some impurities from burner. And this is some results, a video with thermal camera. And also we measure the temperature in different position of the flame. And the green one is the results of hydrogen, and the red is results of the propane. And T1, I put here only the results of T1 and T2. You can see here that the temperature of the hydrogen is higher than propane. And also another observation from the burning, we understood that the flame speed of hydrogen is higher than propane. And the interesting part of the project, it's a micro explosion. For this reason, we built again a small setup. Again, from a gas cylinder regulator, explosion chamber. Explosion chamber with pipe and different 3 valves. We add hydrogen and compressed air from here. It's a plastic tank in 6 to 8 liters. And also we put some fan because of density of hydrogen is very low, and we want to have a good mixing inside it. And we put igniter, adjustable to change the position of the igniter. And we only use regular camera to monitoring. And this is the video from explosion. And other, it's very fast. It's very fast reactions. And also what I find out from slow motion, the flame comes from the explosion is large. And also there is the differences between burning in burner. I mean the flame color, it's completely reddish color. And I don't know. We have to do some more experience to find out and find the reason of the differences in colors in explosion and burning. And another observation is we have 2 zones of explosion. Explosion divided in 2 and from the point of the igniter. And the interesting thing also is we try to repeat our experience with propane, with knowing that it's a very narrow flame, have a very narrow limit for flame, but we couldn't do this explosion with this setup. And we pour hydrogen in different concentration, but we couldn't explode with, even with adding a little propane in the chamber, we couldn't explode it. And also we want to do some more experience for this field. Yeah. Until now, what we did, we learned to manipulate hydrogen with burning of hydrogen in a small case and with having a micro explosion. And for the next step, we want to do for burning process jet firing in different pressures and nozzle diameters. As I mentioned, we want to measure length of flame collecting data for modeling and monitoring obstruction and environment for jet firing also. For explosion, we want to measure blast pressure, recording with high-speed camera, collecting data for modeling, and monitoring obstruction and environment. For ammonia, we want to burn pure ammonia and ammonia with other fuels. And for explosion of the methanol, we want to first micro vapor cloud explosion to learn how we can manipulate methanol, and then go to larger scale. Yeah, that's it, and thank you for your attention.